We're going to talk about the origin of the universe. There are two views about this. There's the scientific one, which said that once upon a time there was nothing, which became unstable and exploded into everything. And there's the religious one that says that in the beginning God created the heavens and the earth. Now, it's no good taking scientists to task for not accepting the latter, because science deals with things that they can measure, see, hear, and so on. And there's no way in which you can measure one-off events or the first causes of one-off events. The evidence supporting the Big Bang, well, there's the red shift. When you look at the light from, should we say, a sodium street lamp, you find that it's in distinct lines if you put it through a prism. Look at it with a spectrometer, for instance, and those lines have a particular energy pattern. And if you look at the sodium lines in a distant star, you get the same pattern, of course, but they've been redshifted. That is, they've been moved to lower energies. And the interpretation of that is that those distant stars are moving away from us, and so you get a sort of Doppler effect, such as the Doppler effect you see you experience in sound when a siren from a police car is moving away from you. It drops in tone. The redshift may not, in fact, be due to everything moving away. Other things have been suggested. It could be that gravity from stars is pulling back light. That has been suggested. Others have suggested, and these aren't religious people, these are people from the Soviet Union back in the 80s, suggested that maybe light is slowing down, that very early on in the universe, light was very much faster. It was suggested by Troitsky, for instance, at the Gorky Institute of Astrophysics, that the light was something like 10 to the power 11 times as fast in the past as it is today. If that's the case, then we would have expected the red shift. Of course, it may be that the red shift does represent the idea of the stars and the galaxies moving away from us, as though we all had bad breath, but that would be a Lord stretching out the heavens. And I read that in the book somewhere as well. And this could be for dynamic stability. Now, if you then extrapolate backwards in time, it all comes to one point, we hope, at some time like 12,000 million years into the past. This may be the case, that it might even look as though that happened. But if the universe were only 6,000 years or so old, as history would suggest, then extrapolating back beyond that time doesn't make sense, even though you can do it. The fact that the numbers work doesn't mean that it represents reality. There is also a second pillar to the Big Bang theory, and that is the background radiation. It was discovered some decades ago now, having been postulated, and it was thought that it confirmed this theory. Maybe, maybe not. The problem is that in the early Earth, the echo of the Big Bang would have had it would not have been the same everywhere in all directions. But when you look at the intensity of background radiation, it's exactly the same in all directions. And that is such a problem that they actually sent up the COBE satellite, the Cosmic Background Explorer satellite, to try and find small variations, and they didn't. And then they did. And they said, right, eureka. The problem was that it was said by people who'd worked on the instrumentation of the COBE satellite that what they'd got were below what the instruments were capable of. And the way they got it was by computer enhancing what they thought might be signal to noise. So although there is evidence for it, which is always put forward, that evidence is by no means confirmatory or conclusive. The problems about the Big Bang Theory, well, firstly, the idea that you get something for nothing. We all know that you don't get out for naught. And secondly, that you get order out of an explosion. We know after September the 11th that you don't get order out of an explosion. Now, this is the explosion of everything. And yet, we tell the time by the movement in the heavens. We have our sidereal year. We have our 24-hour day, and so on. We set our watches by it all. Something for nothing goes against the first law of thermodynamics, which says matter and energy cannot be created or destroyed. That seems to beg the question, but really what we're saying is that in today's world, in our experience, in our observations, in our laboratories, you can't get something out of nothing. The order from an explosion goes against the second law of thermodynamics, which says that entropy increases without an input of directed energy plus information. Now, that means, in fact, that things go from order to disorder. So the Big Bang Theory does go against the two fundamental laws of science, which could be regarded as a bit of a drawback. Regarding getting something for nothing, in The New Scientist, Dr. Darling has said, "Don't let the cosmologists try to kid you on this one. They've not got a clue either, despite the fact that they're doing a pretty good job of convincing themselves and others that this is really not a problem. But there is a very real problem in explaining how it got started in the first place. You cannot fudge this by appealing to quantum mechanics. Either there's nothing to begin with, in which case there's no quantum vacuum, no pre-geometric dust, whatever that is, no time in which anything can happen, no physical laws that can affect a change from nothingness to somethingness, or there was something, in which case that needs explaining." The idea of getting an input of energy like a Big Bang producing order, well, we all know the proverbial bull in the china shop. Here he is. Undirected energy cannot produce order. Now, if you want to increase order, for instance, you sow some seeds, well, it's not just an input of energy from the sun and water and nutrients and so on. It's the information coded for in the seed, which is then going to increase the order and produce the plant. And of course, in time, the plant wilts and dies, according to the second law of thermodynamics. Scientists talk cheerfully and with immense confidence about the first few thousandths of a second of time, but secretly most people believe that they're making it up as they go along. That from The Guardian in March of 1997. In a scientific journal, Nature, perhaps the most prestigious of the popular scientific journals, August 96, they say, "Questions about origins have always held a strong fascination for the intellectually inclined, perhaps because such one-time-only events are difficult to study, so providing a vast playground for unbridled speculation and almost limitless armchair philosophy." Isn't that the case? There is a problem with the Big Bang in that initially, if you are creating something of extremely high energy, atoms are not stable at very, very high energy. And so you're dealing, in fact, with just energy radiation and what we call subatomic particles. Protons and neutrons, electrons, quarks, and things that go bump in the night. Now, as they all fly away from one another into space, they get further and further apart with less and less probability that they will interact. And yet, when we look at the evidence, we have the planets all around us and our sun. We have outside of our solar system the other galaxies and clusters of galaxies. And you wonder, well, how did they all come together? How did the subatomic particles get together to form the atoms? Well, this is a problem. And so we've got round it by inventing cold, dark matter as a source of gravity. And it's estimated that something like 99% of the universe is made up of cold, dark matter. It's dark, and so you can't see it. It's cold, and so you can't detect its radiation. But it has to be there because, after all, we have our galaxies. This quotation says, cosmologists have fitted their theoretical universes with some kind of invisible dark matter to help galaxies to form. But for dark matter, nor for inflation, the idea that space spreads out rapidly, is there true independent support outside the cosmological arena for which they were invented. In other words, it's all in the mind of the cosmogonists. That also from Nature in April of 1992. And if you think that's a bit out of date, New Scientist September of 2001 says, nobody has yet detected any such dark matter particles, so the case is still open. Also in April of that year, last year, New Scientist quotation again. Anything in quotation marks is a direct quotation from scientific literature, and things like Nature and New Scientist are written by people with an evolutionary viewpoint. It says, like ghosts, dark galaxies may be a figment of the imagination. If so, and this is important, if so, our theories of how galaxies form are wrong. And we may have to change our ideas about what makes up most of the matter in the universe. If it's not cold, dark matter, what is it? Or rewrite the story of the universe's first moments. So although you'll be told in popular television programs that of course it was the Big Bang, and it was a long time ago and a long way away, so nobody can prove it or disprove it. In fact, the real experts writing in the scientific journals say we could be wrong. Now, there is another difficulty. I'm pointing out the difficulties before I go on to talk about the religious view. When energy produces matter, you get an equal quantity of antimatter, so that for every electron, you have a positron. Now, electrons have got a negative mass, and a negative charge, and positrons have a positive mass, and so on. They're positive charge, and their masses would be the same, and the same goes for protons and antiprotons and so on. And in the laboratory, somebody got a Nobel Prize for actually converting energy into equal quantities of matter and antimatter, and then these two coalesced again immediately to produce the same quanta of energy that you started out with. So nothing was lost, nothing was created or destroyed. But you cannot get just matter on its own, and yet in our solar system, at least, anywhere we've been able to look, all we've been able to find is matter, no antimatter. And the Big Bang could not make matter alone. People come up with wild ideas for this dark matter. In New Scientist in 1997, for instance, it said that CDM may be wiggly lines of stringy stuff. This is tying it all together, of course. That stretches millions of kilometers across space, and super heavy pretzel-like knots of energy. Now, what evidence is there? Well, of course, there's the mathematics. It works. But more recently, in a book by Eric Chason, Cosmic Evolution, published by a respectable press, Harvard University. It's American, but never mind. In 2001, it says, and although the theory of superstrings is now causing great excitement in the physics community, there is to date not a shred of experimental or observational evidence to support it. So although you get these quaint ideas, way out ideas, I'd say, the evidence isn't there, out there. You can't look at a telescope and say, oh, look, string. Somebody else has suggested in his book Hunting Down the Universe in 1997 that 99% of the mass of the universe is in the form of black holes, each the size of a double bed. What happens to you when you go to bed, I don't know. New Scientist in January of this year says, nobody has ever seen a black hole. But never mind the lack of physical evidence, there are enough problems with black hole theory itself to make their existence seem implausible, to say the least. Now, there's a lot of superlatives in that sentence. Enough problems in black hole theory itself to make their existence seem implausible, to say the least. And concludes that black holes are a bag of contradictions that don't make a good case for their own existence at all. So it's not just that nobody's found them, but that the very theory itself is implausible. Remember that if this dark matter doesn't exist, we've got to think again about the first few moments of the universe. The truth is, says Abraham Loeb, Harvard Center for Astrophysics, quoted in New Scientist in February 1998, the truth is we don't understand star formation at a fundamental level. So let's leave dark matter and talk about how did stars form. Well, we don't understand. Star formation, he says in the same article, is shrouded in mystery. Generally speaking, a star forms when a cloud of gas collapses under gravity. However, if the cloud is too hot, pressure will combat the effect of gravity and prevent the cloud from collapsing. So to form a star, the gas cloud must have a way of cooling down. And this isn't as easy as it sounds. In today's universe, this is accomplished by a huge array of molecules which collide and radiate out their heat. However, the atoms necessary for making all but the simplest molecule, that's molecular hydrogen, have to be made inside stars. So to make a star, you need a star, you see. It's a chicken and egg situation. How did the first stars come about? If the first stars did manage to coalesce and were composed of only hydrogen and helium, which are the two simplest atoms, the evidence is missing. No such protostars have ever been detected. All stars that people have ever looked at with their spectroscopes through their telescopes have had heavier, massive atoms present as well. So they're not protostars. Now, by the theory, stars burn by fusion and form heavier elements such as carbon, nitrogen, oxygen, and iron. Incidentally, our own sun should be doing this, but in doing so, the process should produce a lot of neutrinos, which are subatomic particles, which generally speaking go through everything, and you have to go down salt mines to find them, to cut out all other radiation. But no one's found much in the way of neutrinos. There's nothing like enough. It's been suggested that the stars, and particularly our sun, are getting smaller. The physical measurement of the diameter of the sun, as measured from the Greenwich Observatory for a couple of 100 years now, shows that it is getting smaller. And that will produce enough radiation to explain all the radiation we get. Now, scientists don't like this, and they say, well, it could be that it's getting smaller at the moment, but it's a cyclical effect, and in fact, it'll be getting bigger again after a while, and then smaller again in a sinusoidal sort of way. But the reason for saying that is that if you explain the radiation of the sun by it shrinking, this is not going to go on for thousands of millions of years. And so you have to say that the sun cannot be very old. And of course, that's anathema. So the theory says that stars burn by fusion to form the heavier elements. And when the fuel is burned up, they're thought to collapse and then explode as supernovae. And these, of course, are observed. They're things wearing out. They're running down. It's thought that the heavier elements are then incorporated in the next generation of stars, such as our sun and their planets. And our solar system was built from the dust of dead stars. And this New Scientist article from last year in September says it's an oft-repeated fact. And I want to point out to you that maybe it's not a fact, but if you repeat it often enough, then people think it is a fact. But if you ask how this dust actually started to form planets, you might get an embarrassed silence. You see, I'm quoting from evolutionists now. I'm not setting up creationist ideas. John Mather, NASA's Goddard Space Flight Center in Greenbelt, Maryland, in the New Scientist in February 1998 says, "We have no direct evidence of how galaxies were formed, how the first stars formed without the help of the prior generation of stars." That may sound Irish rather than American, but how did the first stars form without the ones before them? But there we are. How galaxies evolved, whether they were formed from aggregations of smaller units or subdivisions of larger ones. And of course, if it was subdivisions of larger ones, where did the larger ones come from? I want to talk now, having talked about the cold dark matter and having talked about the problems with the origin of stars and galaxies, I want to talk a little bit about the age and the size of the universe according to our Big Bang theory. Now, a little bit of mathematics for you. The Hubble constant. Edmund Hubble was a famous cosmologist in the 1920s, and he produced his constant, which says that it's equal to the speed of recession of objects divided by the distance away of the object. So if you've got velocity over distance, that's 1 over time. So if you turn it upside down, the reciprocal of the Hubble constant is a measure of the age. Now, how do you find the distance? Well, distances in astronomy are too great to be measured by trigonometry, and so they've got to be estimated. You see, if I wanted to know the distance to that camera over there, for instance, I'd walk to that side of the stage and measure the angle. I'd walk to that side and measure the angle, and I'd then draw a triangle and work it all out by trigonometry. Because the distance of the orbit of the Earth relative to the Sun is only 2 times 93, that's 186 million miles. It's not anything like a big enough base to deal with things which are, say, 4 light years away, like Alpha Centaurus, and that's the nearest one. So you have to estimate. How do you estimate? Now, you use the brightness of Cepheid stars to estimate the distances. But then the problem is, and this is highlighted only this year in New Scientist, the amount of dust in space is not well known and can vary from one area to another. So if you're trying to measure brightness and you've got a load of dust in between, you're going to get the wrong distance. And so it concludes that at the moment, astronomers have no way of judging distances accurately. I could have left off accurately. I think it would have still been okay. And I think it's John Maddox, who was the editor of Nature back in 1995. He said, because he knew that the various experts had their own ideas of this Hubble constant. Some people worked it out at such, and some people said, no, it's not that, it's something about twice as much as that, or half as much as that, and so on. And he says that the pity is that whilst discordance persists, cosmologists will not know which way to turn on questions like the reality of the Big Bang. So he is also doubting the reality of this scientific method. So let's look at the age of the universe and see some of the reasons for supposing that maybe 12,000 million years is a bit of an overestimate. Well, there's the spiral arms of galaxies. They're winding up, of course, as they rotate. Perhaps they should have wound up altogether by now, if it was really as old as that. There are the short-term comets. Now, this is a comet this is a composite, actually, of several observers taking their videos of a comet that was recently over America, and it goes over the eastern seaboard of the United States. There she goes, and it lands in a car park. Comets are dirty snowballs, and as they get near the sun, and in their orbits, they get close to the sun, and then they go off in an ellipse way out into deep space, and then come back again. And each time, the snowball loses some of its dust and vaporizes itself. And you see that trail, such as we saw there, made up of ice particles and vapor, water vapor. And so eventually they fall apart. And it's said that the famous Halley's Comet is now in several pieces. They've sent probes up to watch it, and probably won't come round again. It means that you have to explain that comets are not as old as the solar system. And that's a bit of a difficulty, unless you can say that, well, actually there's a place where comets reside, and the Kuiper belt, and further than that there's the Oort cloud. But the problem there is that the Oort cloud is so far away that it would be impossible to see comets out there anyway, and so it's all again in the imagination of Professor Oort, the late Professor Oort, who may know differently now. We've never actually seen the Oort cloud, says the Scientific American for September 1998, but no one has ever seen an electron either. Now, that's an argument for you. Electrons are things that you can measure the charge-to-mass ratio of. You can do reactions with electrons, and the whole of chemistry is based on reactions of electrons. So it's very different from Oort's cloud, which you can't measure anything of and you can't do any reactions with. So that is typical of a facile statement which means nothing. Another thing about the age of the universe: the Earth's magnetic field is decaying. It was first measured in 1835 by Gauss, and Gauss has given his name to the unit of magnetic field strength. It's been measured ever since, and it's measured today, of course, and it's found that it's decreasing all the time, and its half-life is only 1,400 years. So that means to say that in 600 years of the present era, AD, I don't think we're allowed to say AD nowadays, are we? AD, year of our Lord, 600, it was twice what it is today, and so fish and migrating birds and so on would have found it much easier, I suppose, and even sailors. And if you go back another 1400 to 800 BC, before Christ, then it was 4 times the present. And if you go back to 2200, just before Abraham's time, not long after the flood, then it was 8 times. And each time you go back 1400 years, you double it. By the time you get back 10,000 years, you're like a magnetic star, which would be a fluid Earth, a molten Earth. Not just the Earth, but Mars has a magnetic field, although it's a lot weaker than the Earth's field. And even things like Ganymede, which is Jupiter's largest moon, has a similar magnetic field strength to the Earth. Now, in defense, the geologist will say, but the Earth's field has reversed several times over the past geological history, and this can be measured. But of course, you're not measuring the field strength. There's no way in which a rock will allow you to measure field strength. It will only tell you direction. And if, for instance, during some cataclysm in the past, such as Noah's flood, the Earth were to be spinning wildly, then you could get very rapid reversals in the Earth's field. And these have been found. For instance, you can have a volcanic sill, and the top of the sill has a different direction from the bottom of the sill, and Newton's laws of cooling tells you that there's a difference in time of about 2 weeks. So it's a cataclysmic, catastrophic reaction. Looking at the age of the universe, we have Saturn's rings. Now, Saturn's rings are comparatively thin compared with their great width. And it seems amazing that these spinning rings, which are shepherded by planets, little moons, could have stayed stable for something like 4.6 thousand million years, which is the way in which scientists say the age of the solar system is. Dust layer on the moon. According to Isaac Asimov, writing before anybody sent a probe up to the moon, there's enough dust landing on the Earth to make it, that if it were to land on the moon rather than the Earth, then, because on the Earth, of course, the winds and the seas and everything incorporated into the mantle eventually, but on the moon where you don't have this weather, no atmosphere, no seas, proper seas that is, then you should have 54 feet of dust. But then, of course, they sent up probes, and then they sent up men, and there was only this few centimeters of dust. And so they said, well, actually, it's just that we got it wrong, that our estimate of how fast it was all accumulating was much too great. It's okay, really. The moon really is 4.6 thousand million years. So you've got these various things that we've been talking about in the last 5 minutes, talking about the age of the Earth. These are reasons to suppose that maybe the solar system, maybe the universe as a whole, is not as old as the Big Bang Theory suggests. Also, maybe things don't happen as slowly as evolutionists suggest. For instance, there's a companion star to Sirius. It was a red giant 1,500 years ago, and that's a matter of observation and history, if you like. It's all recorded. And now it's a white dwarf. Now, this decay from a red giant to a white dwarf has happened in 1,500 years, not millions of years. It's a decay process. There's a leading British astrophysicist called Michael Wolfson, and he's written in Physics World in May 1996 with 3 problems with our solar system and how it was formed. And he said these are real problems which are generally overlooked. Here's 2 of them. The first question is how partitioning of the material was achieved, whereby 0.0014, that's 0.14% of the total mass, that's the planets, ended up with 99.5% of the total angular momentum. In other words, the sun should be spinning very rapidly, hundreds of times faster than it does, according to the nebular theory. Here's the nebular theory. A hot cloud, the sun, it forms from the denser material at the center, and bits of cloud then thrown out to the sides, but the sun should be spinning very fast at the center, and there we have the planetary system of our solar system. That's a problem, he says. That's the first question. Next, we ask how the planets or planetary cores would form. And he leaves that open to question as well. And the final question, he says, rarely considered, may be the most challenging. He says the spin axis of the sun makes an angle of 7 degrees to the normal to the mean plane of the solar system, and that's virtually defined by Jupiter's orbit. Even if the mass angular momentum could be achieved, that's his first point, then how could this 7-degree inclination come about? The physics doesn't allow it. Not if the solar nebular theory is correct and the sun and the planets all come from a hot gas cloud condensing. He says the solar nebular theory is beset with difficulties and in some respects appears to be unsatisfactory. Definitely unsatisfactory, he says, and he's a leading British astrophysicist. So, you've got all these problems with the Big Bang Theory. And then, of course, if everything in the solar system came from one cloud of gas, then you'd expect that gas on one planet would be the same as gas on another. But in fact, the ratio of nitrogen isotopes of mass is 15 to 14. 14 is the normal one. Nitrogen gas, you remember, is what makes up 80% of our atmosphere and keeps us from burning. The ratio of these isotopes on Jupiter is only 2/3 that on the Earth. It's not as though they're just slight differences. No, this is a major difference. And so the two planets are unlikely to have been formed in a common nebula, according to New Scientist of June last year. So, what have we seen? The professionals are unhappy about their theories of the Big Bang, dark matter and black holes, galaxy and star formation, solar nebular theory, age of the universe. So that's the scientific case. And we have to ask, it's just possible, I suppose, that it was designed, and this religious case is in fact true. In the beginning, God created the heavens and the earth. And as we saw, the problem is there's no way of proving that scientifically. So we can't really go along with that. But there is evidence. Even the scientists recognize that there is evidence. They call it the anthropic principle. Anthropos is the Greek for man. And they say that it's almost as though the universe was specifically designed for man to live on the earth. Isn't that amazing? Could it possibly be? The anthropic principle recognizes that the fundamental constants of the universe, the gravitational constant, which is the same, of course, presumably all over the universe, as far as one can tell, the relative masses of protons and neutrons, etc., they're the two main particles that make up atoms. For instance, nitrogen is just one proton, and deuterium is one proton plus one neutron, and so you could go on. The gravitational constant, the relative masses of protons and neutrons, etc., are fine-tuned to the existence of life. And the simplest explanation, the Occam's razor explanation that should be taken as true, is that a master designer created it all as a complete package. If the proton were just 0.2% heavier, there could be no hydrogen atoms. That means no stars, no water, no biology, and so on. Then the gravity force is precisely inversely proportional to the square of the distance. All right, so G is proportional to 1 over r squared. And it's not just 2, r to the power 2, it's r to the power 2.000 repeating. Otherwise, the universe could not hold together. It's not just me saying this. This is mathematicians and physicists working it out. There are other things about the anthropic principle that we could look at. The position of our solar system in the galaxy is optimal. You can see in the background here a galaxy which is made up of spirals. Now, if we were close to the center of the galaxy, the spirals, then there'd be a lot of stars all the way around us, day and night. That wouldn't be so nice, would it? If we were right out on a limb on the edge of the galaxy, then the night sky would be pitch black, and that wouldn't be too interesting either. And we've seen, while I've been presenting this, a number of beautiful examples of star clusters and nebulae and so on that are, it's not just convenience and giving light in the right proportions, but it's beauty as well. The Earth's orbit around the Sun is circular rather than elliptical. Now, you imagine what it would be like if it was seriously elliptical, asymmetric, that when we got close to the Sun, it would be unbearably hot. When we got further away, the opposite. The Earth, if it were 5% nearer the Sun, the seas would boil. Just 1% further away, and they'd freeze. Our daily rotation rate. It's ideal for temperature. It's ideal for sleep patterns. See, if the Earth were going round on its axis at only half its rotational speed, then you'd have a 48-hour day. And that would mean you'd be awake for 24 hours and asleep for 24 hours. You'd have to wake up in the middle of the night to have another meal, or 3 meals even, some of them. And then how hot it would get during that 24 hours of daylight, how cold it would get at night. And then there's our moon. Now the moon stirs up the seas. It gives you the oxygen in the upper layers of the ocean, which then diffuse down and are able to produce the plankton, which are at the bottom of the food chain. And so you get the whole of life in the oceans. The beaches down here at Portsmouth would be absolutely filthy if it wasn't for the moon, stirring up the water twice a day. It also provides a calendar, of course, with our new moon, our full moon, our half moon, and so on. It's not a new moon, by the way. It's the same one all over again. Anyway, the massive planet Jupiter shields the Earth from comet bombardment. You remember the Schumacher-Levy comet that broke up into umpteen pieces and then spiraled into Jupiter under the massive gravity of Jupiter. If Jupiter hadn't been there, we might have got the bits instead. You see that the solar system is made for man. Gonzalez, University of Washington in Seattle, writing in New Scientist, June 1999, says, "So what's so special about our sun? Firstly, it's a single star, whereas most stars are in multiple systems. That would play havoc with our orbit around it, wouldn't it? Then again, the sun has about a third of the variation in brightness found in most other stars. I think that our sun is extraordinarily stable. We seem to have found a star that's extremely stable and friendly to life. Did we find it? Or we're just on a star that happens to be stable right now, but I don't want to worry you. Many other stars in our galaxy regularly emit super flares 10,000 times more powerful than the sun's emissions. And we're very comfortable with our sun, aren't we? Coming down to Earth now, the soil, the minerals, the ores, the wonderful balance of metals and fuels and soil and everything. The hydrospheres with the rivers, the seas, the cycles that were explained by Solomon in Ecclesiastes 3,000 years ago. The atmosphere with its proportions of oxygen, nitrogen, and carbon dioxide. You know, the plants build their cellulose by absorbing carbon dioxide, and in doing so, they give out oxygen. And so if these parks that you find in towns, they're like the lungs of the town. And the animals, like ourselves, they take up oxygen and give out carbon dioxide. And if there were too much carbon dioxide, we'd all be smothered. If there was too much oxygen, and not too much more than we have at the moment, then forest fires would be much more prevalent. And if there was less oxygen and more nitrogen again, we'd find it hard to breathe. And so you've got the soil, the hydrosphere, and the atmosphere are all excellently suited to support plant and animal life. So this isn't scientific proof that God created the world, but it is evidence of an anthropic principle which supports the idea that God created the heavens and the earth. Here we'll put it in mathematical terms. This is a fantastic quote from New Scientist of May 1997. It says that physicists calculate that the probability of our universe having the ingredients of life purely by chance is about 1 in 10 to the power 229. Now, there's something of the order of 10 to the power 80 particles in the whole of the universe, the observable universe. So 10 to the power 229 is quite inconceivable, as is, of course, 10 to the 80. Because every time you add one more naught, you're multiplying the whole lot by 10. To argue that mathematics alone can win us that minuscule chance is in the end no less mystical than invoking a divine creator, says the New Scientist. Mathematics becomes the creator. Isn't that a fantastic quote? It's such a minuscule chance that things are the way they are, that if you're going to argue that this is just a mathematical, just an improbability, but it happens to be right, then that's as mystical as saying, well, there was a divine creator, what done it? There has to be a way out of this for the evolutionist. Well, Dr. Michio Kaku of New York, author of Hyperspace, A Scientific Odyssey Through the 10th Dimension, and it's published by Oxford University Press, 1995, he suggests the following. In the beginning, there was nothing, which was unstable, began to decay and boiled, with billions of tiny bubbles forming, and each expanded into a universe. You know when you do the washing up, chaps? You put in your fairy liquid, and you whoosh it round a bit, and up come all these bubbles, and they say, you don't need as much as that. Go away. And well, bubbles in Kaku's multiverse are joined by wormholes connecting with black holes in each one. This is imagination gone wild, isn't it? Our universe is the 1 in a billion. Well, it's actually the 1 in 10 to the power 229, which is fine-tuned for life. And you have to say, in favor of this idea of somebody perhaps going down a black hole through a wormhole and finishing up in another universe, Lord Lucan hasn't turned up, has he? The late Sir Fred Hoyle, who was Astronomer Royal in his day, he says in his book, The Intelligent Universe, the picture of the universe and the formation of the galaxies and stars as it has unfolded in astronomy is curiously indefinite, like a landscape seen vaguely in a fog. A component has evidently been missing from cosmological studies, a component involving intelligent design. He's looked at the odds, and he's talked in terms of blind men and Rubik cubes, and he says there has to be an intelligence there, the intelligent universe. It's estimated that the observable universe contains 400,000 million galaxies, each containing thousands of millions of stars. And you could compare that with the number of grains of sand on all the seashores. And I've got this book that says that they are comparable. This book also says in Isaiah chapter 40, lift up your eyes on high and behold who has created these things that brings out their hosts by number. He calls them all by names, by the greatness of his might, for that he is strong in power. Not one fails. And you have these beautiful structures like this galaxy photographed somewhere or other in the universe, and these fantastic number of stars. He is great in power. Amen to that.